There we go. Thank you. All right. All right. All right. So YouTube is up, and this actually makes it possible for me to look at the lag time between YouTube and Discord, between the YouTube and the real time, and it's actually pretty bad. It's about 15 seconds. So YouTube is about 15 seconds behind Discord. So if possible, use Discord. If not, like if you're using a mobile, and I think the Discord mobile app does not do live stream, that may be a limitation. Or I think it's the browser. That's it. It's the browser that doesn't do live stream. All right. And Sakio is typing something, probably related to which one does not do live stream. Oh, okay. Okay, so Discord mobile does work, but it makes it kind of difficult to see the actual screen. Oh, okay. Excellent. Yeah. Okay, thank you, Sakio. All right, so getting back to this program. So what this line is doing is really the same thing as k equals to, and then I plus equal j. Okay, so these two lines are basically equivalent, even though the first one looks kind of cryptic, but they are really doing exactly the same thing. And the way it gets done is we have to pass a pointer to an unsigned to assigned integer this time, and then a value that is passed by value. Okay, so we got a pointer and an actual integer. I have a local variable t over here, which is not really needed, but I just put it in here so that I can illustrate how to use a local variable. And then what we do with the local variable is we compute what the result is supposed to be. Oh, actually, I forgot one thing. Okay, px equals to t. All right, so the right hand side where the cursor is right here is computing the sum of the integer the px is pointing to. So px as a parameter is a pointer, and then v itself is really just an integer. So I'm adding two integers, and whatever the sum is, I store it into the local variable t. The local variable t is used in the next line. On the next line, I use local variable t to update not the parameter px, but where it points to. Okay, because px is a pointer. If I were to say px equals to t without the asterisk, the compiler would have compiled an about type mismatch, because one is a pointer, the other one is an integer. Assignment does not work across these two different types. And then the last line is just so that the function itself also returns the same value as t. So if you look at this line here, I is updated just because of I plus equal to j. The plus equal operator is called a compound assignment operator in C and C++, so it already modifies I. But the plus equal operator is an operator, which means it returns a particular value. The operator itself has a value. That value turns out to be the value of I after it is updated. So k equals to this particular expression is really the same thing as k is now the same as I. Okay, so if I were to just do this and then I say k equals I, that would have accomplished exactly the same thing as the previous form, but I want to keep the previous form because this one is identical in terms of what it is actually doing with the function call. So do we have any questions about the C code that we are gonna take a look today, especially the definition of function f? So I'm gonna give you guys a maybe 20 seconds or so to think about questions, and if there are no questions, then we'll continue with the lecture. Okay, sure. Yep, we can. This program is runnable, so we can definitely run it in GDB. Okay, that's one request. All right, so cool. All right, so we'll continue the explanation using GDB, and here's main. So when you look at main, it doesn't really do much. It has got two local variables. One is I, one is j. I itself is initialized to 7. And then let me turn on line numbers because this way I can refer to the line number. On line 17, the first thing we do is we call f, right? So we call f using the address of I to pass to px, the parameter, and then we use the value of I, which is now 7, to pass to parameter v. And whatever f is returning is stored into our second local variable of main, which is j. And then on line 18, we just return a 0. We are missing a semicolon. Okay, so I just caught it. This is the thing about programming in different programming languages all the time is, in JavaScript, the semicolon is not needed. And usually people say that do not use a semicolon because I have no reason, no idea why, but the recommendation in JavaScript is not to use the semicolon to separate the statements. So anyway, this is a program that actually runs. So we'll go ahead and see how it runs, and we'll trace it line by line in C and C++. So this is kind of what you might want to do too, is with today's lab, you might want to look at the C code because it does compile, or if it does not compile, you can make it compile by adding a main function to it. So the idea is to run the programs in C first, okay? Use GDB, if you are comfortable with command line tools, or if you're not, you can use code blocks, you can use, what is the other one? GDB Online, I think. Online GDB. I cannot remember the name of the website, but it's one of those I have already mentioned. So you can actually just use a browser and be able to use a GDB on the C program, especially with a program that is like this, which is monolithic. It is a single file program. So the idea is to understand the concept in the high level programming language first before you even try to translate it into assembly. All right, so let's go ahead and compile this program and then run it in GDB. So gcc-g to include debug information. I can do a warn all. It's going to complain about the two local variables in main. I put values into them. Well, actually only one of them, j. I put a value into local variable j, but I did not actually make use of local variable j. So GCC is going to complain about that as a warning, but it's good to turn it on, okay? Because so right there, it complains about local variable j is set, which meaning it got a value, but it's not used, meaning that it is not referred to, read-only manner. So, but that's okay. Okay, this is just a test program. It is not a big deal. So now we'll use GDB to actually run the program. It's called PE because it's plus equal to. Okay, it's just describing the operator. So we'll list the program. I'm just using L to list the program, and we'll put a breakpoint on line 17. I think line 16 is not worth a breakpoint, so we'll start with line 17. And now we run the program. We stop on line 17, and the dark red may not show up very well on. It definitely won't show up, on a projector, but is that okay? I mean, do I need to change the color scheme to make it? Can you guys all kind of still read the program, even though it's using some really dark color for color highlighting, syntax highlighting? Okay, nobody is complaining. All right, so if no one's complaining, we can go ahead with this. Looks fine. Oh, okay, thank you. Thank you, Jared. All right, so we'll single step here, okay? Single step is S. And as soon as we single step, now this is, the nice thing about GDB is when you're single stepping and you're calling a subroutine or you're invoking a subroutine, oh, it's not really okay? Is that what Julian is saying? Julian. Okay, I can change the color scheme. Let's see. Go to preferences and then go to colors. All right. So it's the darker colors that is a problem. So we can yeah, well, YouTube and versus Discord really should not make that much of a difference. All right, so is that better? I think that should be slightly better. So I'm gonna continue with the discussion here. So when we look at the invocation, it tells us that px is this big number here, and that is just an address, or the red is difficult to see. All right, let's see if we can fix that. Yeah, it has got some built-in color schemes, but some of these built-in color schemes don't really work well. Um, nope, that definitely does not work. I'm just going through the list to try to find one that works. This is the default Xterm. I guess it works okay, except now some of the lighter colors gets difficult to see. Yeah, alien blood. Yep, yep, yep. Well, in that case, I guess we wouldn't be using Xterm. We'll be using Xfile instead of Xterm. All right, so here we got parameter px. Parameter px is an address, and this is what an address looks like. At least in this particular operating system. The \a, is actually referring to the value that the pointer is pointing to, which is basically 7. V as a parameter has a value of 7, and we know that because I was initialized to a value of 7, and then we pass I by value as the second argument when we called f. Okay, so now we get to line 7, and line 7 is in the subroutine, which is right here. So what we are doing is the \a is an escape character because 7. Okay, so let's go back a little bit. This particular type, int 8 underscore t, is an 8-bit signed integer, which is exactly the same thing as a char. So when you're looking at a char or a character, ASCII code 7 is one of the control characters, and as a control character, it is not printable. And because it's not printable, it's using a backslash and an A to indicate that particular ASCII code. So I can illustrate that concept. Let me just go to a new terminal. Maybe here. That's fine. Okay. So in Linux, if you do a man ASCII, it will tell you what each character is. So we can see that the character code 7 is corresponding to a bell, which means if you were to use a teletype terminal and you send the ASCII code 7 to the teletype terminal, it would have rung the bell on the typewriter. I mean, literally, there's actually a bell in the teletype terminal, and the ASCII code 7 is basically telling the typewriter to ring the bell. But because we cannot display a bell, okay, when we print a string, which is what chars are usually for, so it uses \a to represent the bell signal. And you might be asking, well, if bell starts with a B, why not \b? It's because \b is for backspace, which is used far more commonly compared to the bell ASCII code. But in this particular context, we are not using ASCII code. We are not looking at the signed 8-bit integers as ASCII code at all. So the \a really does not apply to us. It is more of the actual value, which is 7, that matters to us. So that's a good question. If you You can try it out, with a dumb terminal, like when you sign into a remote terminal. You can try to do an echo, and then Control V, which is the escape, and then Control. Let's see, I think the bell signal is Control G, and then press the Enter key, and you can probably hear the dumb terminal, giving you a beep, which is what the bell signal is like in a modern computer. So, let's go ahead and print certain things. Okay, so px is a integer pointer. Okay, it's pointing to a location, and when you look at what it points to, or the value of the location that it points to, it is 7, which is also known as a \a, because GDB wants to be helpful and is thinking, hey, it's an 8-bit signed integer, maybe we should look at it as a character, which in this case is really not the case. We really just want to look at the integer value of 7. We don't really need to look at the ASCII code interpretation of exactly the same bit pattern. All right, so that's that. And then when we look at v, which is the second parameter, it is also 7. So it's not really surprising that the sum of 7 and 7 is actually just 7. So when I single step line 7, now that is completely coincidental. I did not plan for this to happen. Okay, so when we single step line 7, adding 7 to 7 and then storing that result into t, then we can look at the value of t, which is not very excitingly 14. Okay, so in this case it uses \016. So let me just explain that before someone asks. So backslash anything that starts with a 0 is an octal number. So this is a base 8 number. So in base 8, the 6 is representing the number of ones, and then the 1 is representing the number of 8 in this particular number. So we got 1, 8, and then we got 6 ones, which adds up to, guess what, 14. So this is an octal number, which is another way to display an ASCII code when the character is not exactly printable. But in this case, ASCII 14 in the ASCII table really doesn't have a particular meaning as far as Unix is concerned, and that's why it is only displayed as an octal number. So we can actually go here and figure that out too. So the second column is our decimal number, and we are now looking up the decimal number of 14, and we can already see the octal number is 016, and the meaning is supposed to be shift out on a teletype terminal. I have no idea what that means. Okay, that it could be something that's useful, back, in the days, but I personally have not used this ASCII code for what it was designated to do originally. So anyway, so now we're getting back to the debugger. All right. So far so good, right? I mean, so far the math is pretty simple. So what we want to do right now, right before I single step line 8, is to say, well, how do we know what px is really pointing to? Because it just says, px is pointing to this location, but exactly what location are we talking about, right? So if we do a list, I'm not sure whether this will work or not. I think it does. So I'm going to list the main program, or the main subroutine, and we can see how px is really the address of I. So that means I should be able to look at the address of I and confirm that the address of I is exactly the same as this number over here. Now the question is, how do I get to I? If I say print I, or the address of I, it's not going to work, because I is not a global variable, it is not a parameter, and it is not a local variable of the subroutine that we're in right now. We're in subroutine F right now. So the current context is referring to the subroutine that we are in right now at this point, and I does not belong in that particular context. So now the question is, well, how do we get to local variable I of main? Well, before we get there, let me just repeat a command that I have introduced already. It's called backtrace, so which is abbreviated as BT. If you really want to spell a backtrace, that works too, but BT also works. So BT shows you how we got here. it shows that the program started in main, and then on line 17 of this program, we end up in subroutine F, which is here, and subroutine F is now is starting on line 8 in this particular program. Or currently we are on line 8 of this program. So it also has this kind of weird hash or pound symbol. Pound 0 is referring to the current context. Pound 1 is referring to the previous context. So we can now use the frame command, frame, and then use the number that is after the pound sign to go back to a previous frame. Now let me explain what I meant when I said go back to. When I say go back to, I do not mean changing the point of execution. It is simply changing the point of view. Okay, so we are still in F. We are still about to execute line 8 after I say frame 1 in the debugger. All that does, okay, frame 1 is basically to say, let's go back to a previous frame and look at things from that perspective. But the execution point has not changed. So now that we are changing our context back to main, we can now look at I. Okay, I still has a value of 7. Okay, and we can also look at the address of I. Okay, so this is the address of I. I just scrolled the other value off the screen, so you can see how it ends with DFFE, and this is PX as a parameter. And you can also see how the address of I of main also ends with DFFE. I mean, the rest of the address is 7 followed by a bunch of Fs. So this is sufficient to let us identify that the address of I is really the same thing as PX. All right, so let's go back to the current frame. So we say frame 0. We're getting back to the current context, which is in function F. And we are about to execute line 8, so let's go ahead and execute line 8 at this point. Okay, single step. Well, we already know what T is, right? T has 14 as a value, so whatever PX is pointing to should now be updated to 14. Now, if I look at PX, it has not changed because we are not updating the pointer. We are updating what the pointer is pointing to. So that means if I say, tell me what is PX pointing to, that is now updated. But wait, hold on a second here. PX is the address of I, so when I update what PX is pointing to, shouldn't I of main also be updated? Well, let's check. So now we go back to frame 1, which is the context of main, and then we print I in this context, and guess what? It is now updated to 14 as well. So these are ways that you can use to kind of understand how a program like this operate, is by single stepping and also by moving the context between the subroutine being called and the caller, so that you can see how an address passed relates to a local variable in this case that actually belongs to another subroutine. All right, so are there any questions at this point before I move on to talk about some more concepts? All right, there are no questions. All right, and if you want me to slow down, you can just type in the text channel and just say that we need to slow down a little bit, because yeah, that's fine too. All right, so let's go back to frame 0, which is the subroutine that we are currently in, which is function F. And what is left to do is line 9, which is a return T. Exactly, you can watch it again. But if I forget to mention something, then watching it again is not going to help, because if I did not connect the concepts sufficiently, then watching it again will still not connect it sufficiently. So I welcome comments and suggestions if I did not mention enough to make all the points across. All right, the use of frame. Okay, that's a very good question. All right, so this is also a good place to kind of talk about what a frame is. So what a frame really is it's referring to a contiguous chunk of memory on the stack, okay, that that contains everything that is specific to an invocation of a subroutine. I know those words are kind of they're all easy words to begin with, but the connections can be difficult. So what we're talking about in this case refers to all the local variables, the parameters, and a whole bunch of other quote unquote stuff that relates to an invocation, in this case, the invocation of f. So the frame definitely includes these items. The parameters, one is px, the other parameter, which is v, the local variable, which is t. These are all a part of the frame of this particular invocation of f. But the frame is not limited only to these particular items. It also includes the return address, which cannot be seen in C, okay, because C is a high-level programming language, and the return address is not easily accessible. It is there, it's just not easily accessible. It also includes what we call a frame pointer, or a copy of the frame pointer, which we are not going to use in the toy processor because we simply do not have enough registers to play with if we use up another one for the frame pointer. But the frame pointer is really pointing to a fixed point of a frame so that we can refer to local variables as well as the arguments more easily. We will continue to talk about this concept, especially when we switch to assembly language programming. When we set up the arguments and also the local variable, that's another chance to talk about what a frame really is. So that's a very good question, but we'll get back to it when we get to the assembly language implementation of this program. All right, so one more thing, okay, so we want to look at the addresses of these items, okay. We want to look at px, v, and t, but we are not looking at the values this time. So we're going to look at the address of px, we'll look at the address of v, and we'll look at the address of t. Okay, and let's see. The way this particular compiler works is a little bit different from what I anticipated, because I'm looking at the addresses and they do not match my expectation, because px is the first parameter and it has an address that ends with C8, which is a higher address. And then v, which is the second argument, it has an address of C4, and the local variable is t, and it has an even higher address compared to the parameters. And that is actually opposite to what we'll be doing, because what we'll be doing is the typical way of how a C program would work. But in this case, because I think the later compilers, I think starting with a 64-bit architecture, for some reason the ordering of items on the stack has changed. If I were to switch back to the 32-bit compiler, then we would see the address of px being lower compared to the address of v, and then the address of t is also going to be the lowest because it is a local variable. So this is not helping. You can kind of ignore what I just said about in GDB, because it doesn't match how we want to do things in this class. All right. So when we single step this program, which is executing the return statement on line 9, now remember, a single return statement in C is actually doing two things. It is specifying the return value, which is t, but it is also passing control back to the caller to continue execution in main. So there are two things to be done when we see return a particular value in C and C++. So when we single step, we are now getting back to main. And now in main, when we look at local variable j of main, now it also has a value of 14, and I has a value of 14 as well. All right, so in terms of the concept, okay, this is what we want to do in our program that we'll be writing today. All right, so let's go ahead and get out of GDB, and we're going to get back to PE, but this time I'm going to open up PE.C and PE.TTPASM side by side, so because we are ready to implement this program in assembly. So the one thing we do is, the first thing we do is a no op, which is mandatory if you want to use the trace analyzer, which is what I intend to do. And then the next thing we want to do is to do a JMPI to main, because I don't want to change the ordering of the definition of the subroutines. So I want to have main to be defined after F, okay? And then we have subroutine F. Oh, that doesn't show up very well, does it? Because that's supposed to be yellow F colon. All right, so now we have to change the color scheme again. And I think somebody noticed alien blood, and we'll give it a try. Ooh, that doesn't show up. That won't show up well, in YouTube. This one looks okay. The only thing that's kind of faint is the pound include, and in assembly everything looks okay. So we're gonna use this one for now until it doesn't work. All right, so in F, we'll talk about this a little bit, okay? And then we'll get to main first. So main also has got a local variable. In fact, it has got two local variables. So now we have to talk about where are we going to put the local variables? Well, part of the answer was already mentioned earlier, okay? Because when I mentioned a frame, I mentioned that parameters and local variables are part of a frame, and a frame lives on a stack. So that means local variables are also living on the stack. But the first thing we want to do is to review what is on the stack at this point, okay? The caller of F is responsible to push the parameters. And when the caller pushes the parameters, it has to push it in quote-unquote reverse order, which means the last parameter is pushed first. So V is pushed first on the stack, then PX is pushed on the stack, then the return address is pushed on the stack by the caller. So this is what we already kind of know from the homework assignment, from yesterday, and also from the lecture of yesterday, is that we know that parameters are pushed on the stack, they are pushed before the return address, and this is how things look like. So when I display things like this, okay, whatever appears on the earlier line has the highest address, and whatever appeared later on, with a higher line number has a lower address. So we know that the caller has accomplished this already, and we also know that register D is pointing to the last item that we push on the stack, which is the return address. So this is how the caller has set up already. So I'll just kind of comment on this. Caller sets up the stack like this, okay? So now that I am the callee, okay, I already have these three items on the stack: parameter V, parameter PX, and the return address. It is up to the subroutine itself to allocate, yes. So D really is the address of the return address. Yes, that is correct. Okay, so I can comment on that here. Okay, comment of a comment. D really is the address of the return address. Okay, but what I want to do as a subroutine is to say, but hold on a second here. Okay, caller, you got your part done. Okay, you have pushed V, PX, and the return address on the stack. But guess what? I got some other stuff that I also want to push on the stack. That's our local variable. So we want, so the callee sets up some additional stuff on the stack, and that is our local variable t. So that means we have to reserve, one more byte on the stack for local variable t. And to do that, we have to move register D over here. So register D can no longer be over here, it has to be moved over here. So the only way that can be done is to decrement the stack pointer. So when we decrement the stack pointer, then the stack pointer is no longer pointing to the return address. Instead, it is now pointing to the last item that we allocate the space to, which is local variable t. So after this particular instruction, decrement d, d is now the address of the local variable t and not anymore the address of the return address. So at this point, okay, I have allocated everything that I need on the stack, but the stack pointer is now 1 byte below where it was pointing to at the entry point of the subroutine because of the instruction decrement d. And this way we got the frame set up. So in our very simplistic processor, the frame is like this. So the frame has got v, it's got px, it's got the return address, and it has got the local variable t, and the stack pointer always points to the last thing that we push or reserve on the stack. So at this point, the stack pointer is pointing to local variable t, and I'm going to use sp instead of d here because this is a concept that is applicable to every single architecture and not just the toy architecture. So are we doing okay so far? Is this kind of helping to explain what a frame is? It's everything that is specific to a particular invocation of a subroutine. Okay, very good. All right. So if I want to access v, px, or t, everything is actually just kind of relative to where the stack pointer is pointing to. In other words, if I want to access the return address on its own, which is really odd that we need to do it, it's really just 1 byte pass where the stack pointer is pointing to. If I want to access parameter px, it is 2 bytes pass where the stack pointer points to. And if I want to access v, it is 3 bytes away from where the stack pointer points to. So instead of tracking these numbers in my head, the stack pointer plus 0 is the local variable t, plus 2 is px, plus 3 is v, I'm going to use labels to do this. Okay, so I'm going to define a whole bunch of labels. So I'll define a label t, and I'll just make it 0. Okay, because the offset from where d points to t is 0. In other words, the label t is not really local variable t. It is basically telling us how many bytes past where the stack pointer points to can I find local variable t. So the full name of this label really should have been t underscore offset underscore from underscore stack pointer. But that's a really, really long name, and I don't want to use really long names, really, really long names like that. And that's why I just abbreviated to the name of the local variable. Is that understood? That t as a label is not the value of the local variable. It is not even the address of the local variable. It is the offset of the local variable from where the stack pointer is pointing to. In other words, this 0 is referring to this 0 over here. So are we good with this concept? Before we move on. Good, we got questions. Yes, most compilers would compile code similar to this. And Sakil said kind of. All right, so can you be more specific about which part is a little bit kind of sure? Um, all right. So do we have any questions about what this frame is? Or let's start from the beginning over here. Okay, so do we have any questions about what the caller is expected to do before we get to the entry point of the subroutine? Is that part okay? No. Yes. Okay. Okay. So the caller is expected to do certain things. If you're a subroutine being called, you can assume the caller has already pushed the arguments on the stack, the last argument being pushed first, which means it has a higher address, and then the return address being pushed last. So that's what we can expect from the caller. Yes. So the caller is not pushed there. The caller doesn't push the variables, it pushes the arguments. So the argument in this case would be v and px. That's the responsibility of the caller, and so is the return address. Yep, that's fine. So so the arguments and the return address are the responsibility of the caller, because guess what? The subroutine being called really have no idea of what arguments should be pushed on the stack. So it is up to the caller to push the arguments and then the return address. So that's why the comment up to this point, this particular line, this is what the stack looks like at that point of function f, which is before we get to the decrement d instruction. What the decrement d instruction is doing is the subroutine itself, function f itself, is now saying, it's great that we got these three things sitting on the stack. I need those, but I also need one more thing on the stack for my own local variable t. So the local variable t in C code over here is allocated by the decrement d instruction, because we are just saying that let's grab another byte from the stack, okay? And I'm going to use that byte or that location to be my local variable t. But when we do that, the stack pointer moved, right? It's decremented, so that it's decremented without storing anything to that location, and that's why local variables are uninitialized, because we just move the stack pointer to allocate a space, but we do not initialize that location. And Catherine is asking, does it matter which order the local variables are added? The answer is not. It should not matter, okay, as long as it is consistent. So the way you allocate, so we'll see that when we implement main as a subroutine. So that's a very good question. So when we get to main, we'll actually we have to decide how we want to do this. Is I going to be the one with a higher address, or is J is the one having the higher address? So we get to make that decision a little bit later. But that's a good question. I think that question will be answered when we get to the implementation of main. But the real answer to that question is, as long as it is consistent, I do not believe the C programming language standard specifies one way or another. All right. So this part here, okay, let me turn on line numbers. So this part over here is basically just saying, okay, I can see how I might want to. Is it still readable? I just decreased the font size a little bit, just so that I can have enough width to type a little bit more. All right, cool. All right, we got some more questions from Discord. I'm just gonna wait a little bit. All right, so pushing allocates an address, but there's no content in it. So yes, so it's not technically a push because we only allocate, but without the st instruction that usually goes after that. In other words, typically when we push, we store a register into the location that we just allocated, but this is now missing entirely because we have no idea how to initialize local variable t, because that's also how it is specified in the C code. So it's just allocated without an initial known value. And this is also why it is very important in a C program to initialize a local variable, because a local variable, if you do not initialize it, it really is just a location that is not initialized. It has the quote-unquote leftover content from the stack the last time somebody wrote to that location. And in some cases, it actually has reasonable values, which is also really kind of bad, because it can mask problems. When the program is supposed to be wrong, it would seem to be working correctly, because that location, that uninitialized location, turns out to have some content that doesn't break a program. So that's a story for another day. So after the decrement instruction, this is what the stack looks like. So line 13 to line 17 as comments is basically saying what the frame looks like at this point. It's a combination of what the caller did and also what the callee has just done. But we got 4 bytes, at this point in this frame. It is basically including all the arguments, all the parameters, the local variables, if they are plural, if they're multiple, and also the return address in this case. Now, in the x86 architecture, we will also have what we call a frame pointer as a part of this, but we are not going to get into it. Okay, so depending on the architecture, depending on the compiler, there may be additional items in a frame, but this is kind of the minimum of what you can expect from the frame. Are we good so far? All right. Cool. All right, so now we'll go ahead and finish up the label definitions. So we got T, we have return address, which is T1 plus. It's basically 1 plus T in postfix notation. And then we have PX. PX is return address 1 plus. And then we have V, which is PX 1 plus. So somebody's going to point out and go like, we could have just said that PX is defined to be 2 and V is defined to be 3 and be done with it, and without using these expressions. That is actually true as well. But if I do it this way and I need any additional local variables later on, because everything is only relative to the thing right before that, that means I can introduce additional local variables without having to change the definitions of at least PX and V. I might need to change the definition of return address depending on whether I want the new local variable to be at the lowest point, or do I want T continue to be at the lowest point. Okay, but PX and V defined as on line 22 and line 23 makes them quote-unquote float with the label definition of return address. So this way I can minimize the amount of changes I need to make if later on I decide to have more local variables in the C code. Is that okay? Does everybody understand the rationale of why I define these labels using these expressions instead of just using a constant? All right. So we are good up to this point. All right, so now this is all for just setting up the frame, okay? V is px plus 2. Yes, we could do that too. So if I want to skip the return address, I could also just say the px is t 2 plus, and then make v relative to px only. So that works too. Is it 2 plus? Yep, it is 2 plus. If I do it this way, then I don't even need return address as a label, which is sometimes helpful. Yes, they're all equivalent. The bottom line is px really is in the end, px is defined to be 2 and v is defined to be 3. The question is, how flexible do I want the label definitions to be? And the most flexible one, okay, now there's another way to do it. Okay, let me show you yet another way to do this. I can now define a label of f local var size. Okay, so this is basically telling me what is the total size of all the local variables of f. And well, that's only one, right? It's basically t1 plus. T is the last local variable defined, and it only has a size of 1. So now when I look at px, it can be defined as f local var size 1 plus. Let me see. Nope, doesn't need the 1 plus. It is just, no, it needs the 1 plus because that one, this one here, is referring to the return address. The return address takes up that 1 byte, and then v is still going to be relative to px. So this is yet another way to do this. Now, let me explain why this is helpful, why it is good to know the number of local variables in it. To do it this way, now let me just remove line 9, the decrement d on line 9. So the way I do it this way is because what if I have a bazillion local variables? If I have a bazillion local variables, then f underscore local var size is not going to be just 1 anymore. It's going to be like 23, 45, or whatever insane number of bytes you're going to use up for local variables. So in that case, a decrement d is not going to cut it because decrement is just decreasing by 1. And I don't want to write some code, any type of macro code that is conditional. So if I just have a generic generic label that tells me how many bytes the local variables are taking up, now I can do something like this. I can just do LDIA with f underscore local variable size, and then I can do a subtraction. I can say subtract a from d to allocate for local variables. So I can just do that. How would you know the size? Do I have to count or set it? So the idea is it is going to be whatever is the last local variable to be allocated as a label, and then plus the size of that last local variable. And in this case, there's only one, so that's why I know that there's only 1 byte that I need to allocate for my local variables. When we get to main, we'll see how this method works, because main has got 2 local variables, and then we'll play with that when we get to that point. So all of these are good questions, but I think we'll get to the answer later on. So I'm going to do something that's kind of odd, which is, it's odd to most people, but it is consistent with what I usually do, is I'm going to do another LDIA f local variable size and add DA over here. The reason why I do this is it's kind of like parentheses. Okay, this is like a pair of parentheses. If I allocate for the local variables at the beginning of a subroutine, I better deallocate those local variables at the end of the subroutine, at the end of the execution of the subroutine. So I'm really just doing the parentheses approach, where at this point I know that stack is quote-unquote balanced, which means the stack pointer is now pointing back to the return address. Then I can do the usual thing, which is LDIA, LDIB. Oh, I cannot use A. I have to use another. I can use B. I cannot use A because the subroutine is supposed to return a value, and the return value is stored in register A, so I know that I cannot use register A at the end of the subroutine. So I can now do a LDBD. Because increment only works when there's only one byte used by local variables, this one is universal. It doesn't matter how many local variables you have. In fact, if you say I don't have any local variables, and f underscore local var size is a 0, it still works because you're subtracting 0 from the stack pointer and you're adding 0 to the stack pointer. So this approach, even though it may consume more space and is time consuming, but it works all the time. Okay, because your local variable size can be 0, can be 20, can be just 1, and it works in all cases because we want to have an approach that works in as many cases as possible. Even though it may not be optimal, it still works. Okay, so we want to get the concept down first in this class before we try to optimize and make the programs go as fast as possible. So what I'm working on right now is the instructions at the end of every single subroutine. Okay, we retrieve the return address, we deallocate that byte used by the return address, and then we continue execution back to the caller. So this is the parentheses approach that I typically do. Is I start with the beginning, I close it right away, and then I go back to insert code in between. Richard is asking, I still don't get how lines 18 and 20 work. Why only add 1? The 1 has to do with I only got 1 byte used for my local variables in the C code. So that's why my local variable size, which is basically the number of bytes used by all the local variables, is just 1 byte. So this 1 is basically the size of local variable t. So I can actually comment here too. So I can say size of t is 1. All right, so there's only 1 byte allocated. I'm not sure what you mean by above the stack pointer. The stack pointer is pointing to that 1 byte that we just allocated for the local variable. You mean below the return address, not above. It is below the return address because when we push additional items on the stack, they have addresses that are lower than the items before the push. Oh, okay. Yeah, the line number is higher, but when we look at the location or the address, it is lower. So that's why it's helpful to look at the offset 0, 1, 2, and 3, so we can refer to the offsets. The offset is lower or the offset is higher. All right, so now we get back to here. So the parentheses that I was talking about, line 22 and line 25, line 24 and line 25 is kind of like open parentheses, and then line 27 and line 28 at this point is kind of like closed parentheses. So now we can actually get into the meat of this particular subroutine. So we are moving on to this line in C code. Let me just turn on line numbers on this side too. So when you look at line 7 in the C code, that's what we want to do. And the first thing we need to do is to evaluate the right hand side. So don't even bother to try to find out where t is or how to store something into t, because we got to figure out the value of the right hand side of an assignment first. So now we run into, oh, we need to get to whatever px is pointing to. So that means we have to get to px first, right? So this is something that we have seen before. Okay, we can do actually, I take it back. We haven't seen this before. This is a new approach of doing things, but it only uses instructions and concepts that we have already introduced up to this point. So we do a LDI, and we look for a free register to use at this point. And at this point, we are not even close to the return statement. So all 3 registers are free to be used at this point. Register A, register B, or register C are fine. So I'm just going to use register A. And what I do is I put PX in an LDI. So now, okay, after this, I will say PA equals to offset from where SP points to PX. Okay, PX the parameter. So let me just make it super clear. Okay. All right, because that's the whole point of that label. Okay, the label px really is just defining how many bytes is px, the parameter, um, away from where the stack pointer is pointing to. So this is just an offset, and then the next instruction is an add instruction. So we add the stack pointer to a. So at this point, a becomes the okay. So if you really look at the long version, so a is now the stack pointer plus offset from where the stack pointer points to parameter px. But that's really a super long way of saying something that is a little bit simpler. That really is just saying the address of px, right? I mean, think about this. Okay, look at the comments on line 28. A is now the stack pointer plus the offsets from where the stack pointer points to px. Wait, isn't that really just saying the address of px? Are we getting this part okay? When we trace this code, it will be very clear of how it works. So right now we're just kind of talking about the concept a little bit. Okay. On line 27, how do we know it's the offset? Because that's how the label is defined. So on line 22, when we define, I take it back, when on line 21, when we define px, that's why we define px the way it is, because we want the label px to be the offset in number of bytes from where the stack pointer points to after the entire frame is set up. Okay, all right. But do we want to use px in the addition in the C code? Nope. Looks like we need to get to what px is pointing to. So register A is now the address of px. It's not even px itself. In other words, we are not accessing the parameter itself. We only have the address of the parameter. So we will use a LDAA, which means register A is now the dereference of the address of px, which is really just the value of px. Okay. Now the value of px is a pointer. Okay, px is a pointer itself, which is also not what the addition is trying to access. The addition wants the value that px is pointing to. We are not adding a pointer to v, we are adding the value of the location that px is pointing to v. So we need another dereference. So now a is the dereference of px. And finally, we got something that looks like what we really want on the right-hand side of line 7 of the C code. So that's one. Now we need to get to V. How do we get to V? Well, we better not mess around with register A, because register A now holds something that is a part of what we need to do. Let's use register B then. So we looked at register B, we use register B, we put V into it first. So now B is offset to parameter V. So I'm just kind of shortcut, I'm abbreviated to just offset to V, which is implicitly offset from where the stack pointer is pointing to parameter V. Okay, but I'm just gonna make it a little bit shorter at this point. Add BD. So when we combine the offset with the stack pointer, B is now the address of parameter V. LDBB. So the B is now the dereference of the address of V, which really is just the value of V. So are we still doing okay so far with this code? It's about the approach, so you don't have to just look at lines 33 to line 35 and focus on register B at this point. All right. Yeah, this will take a little bit of time. When you just look at the source code, it is a little bit harder to really get a good grasp of what things are because you're not looking at concrete numbers. When we run this code through the trace analyzer or the CLI mode first, yes, absolutely. I will share the code at the end of the class, but more than that, I will assemble the code and run it in the CLI mode of Logisim, and then we collect the trace log, and then we'll run it through the trace analyzer. And that is where things will start to become more clear because you can actually get to see the values inside the registers, each one, and figure out what each line of code is really doing in this particular program. So that will give you the insight into how this works. Okay, a little bit more of that. So let's continue with this. So we just need to add instruction. Which way we are adding, add AB or add BA, doesn't really matter as long as we know which one is the correct one. So A is now whatever PX is pointing to plus V. Line 31. It is needed to get to what the pointer is pointing to. So right after line 30, register A has the parameter itself, but not what it points to. So line 31 is taking the pointer, our parameter, which is a pointer, and dereference the pointer to get to what the pointer is pointing to. So line 31 is not to get to the pointer, it's to get to what the pointer is pointing to. Yes, so it is the actual value that we want to use in the addition of line 7 in the C code. Line 31, yes, so line 31 is doing the explicit dereference that we see in the C code. Yep, all right, cool. All right, so continuing on to line 37. So line 37 has finally completed the right-hand side, which is this portion in the C code. So now we need to store that into local variable t. So let's try to figure out where t is. LTI register B is now free to use again because we have already computed the entire right hand side and stored that into register A. So I can now reuse register B. So I put the offset to access local variable t into B. So B is offset to local variable t, add BD. Whoa, hold on a second here. We just did this to access parameters. Can we really do the same thing with local variables? Absolutely, because local variables and parameters, they're all sitting in a frame, and the labels are basically defined to be the offset in number of bytes to access each item on the stack in the frame from where the stack point is pointing to. So this approach works not only for parameters, but it also works for local variables. It is very universal. But this time we don't want to do LD after we get to the address of t, because the way t is used in the assignment here, this is what we call a L value of an assignment, or the left value of an assignment. So in this particular case, we don't want to get whatever t has. We want to store to t. So instead of using an LD, we need to store to whatever B is pointing to. And can someone tell me what the second operand needs to be? In other words, where the cursor is currently located, what register should I use on line 41 to complete this particular mnemonic? Register A, very good. So register A is the value of the right hand side, and register B is the left value of the same assignment. So this is going to get the job done. Okay, so this is getting this line of C code done because register A has the right hand side value, register B has the left value or the L value, and a single store completes the mission. All right. Yep, so all this code from line 27 to line 41 is just implementing line 7 in the C code, but it illustrates the concept. Okay, you can see there's a lot of repetition, right? So on line 43, we'll start to deal with line 8. Okay, so we'll do a LDI. So register A and B are both free at this point, so I've got to reuse register A. Now you might say, oh, we just store into register, we just store to local variable t, and register B is still pointing to local variable t, so we can just really use it, right? The answer is yes, we absolutely can use it. But what we'll do right now is to pretend that every statement in C starts from scratch. In other words, we are not optimizing anything. We're just saying, let's just blindly translate the code from, with each individual statement without reusing things that are already in the registers. Okay, because we are now trying to practice, right? We're trying to practice how to get things done. So on line 8, the first thing we need to do is to get to the value of local variable t. So once again, okay, A is the offset to t, add 80. A is now the address of t, which is not really what we want. We want the value of t. So we have an LDAA. So now A is the dereference of the address of t, which makes it the value of t. That's my right-hand side. Then we move on to the left-hand side, which is a little bit more ugly this time because it is the dereference of px. Alright, so Sakil said, so this is what IDE do for every line of code in C and C++. This is actually what the compiler does. Okay, so we are basically, I'm acting as the organic C compiler. I'm looking at the C code and I'm translating the C code into the assembly code. So it's not so much the IDE, it is the job of the compiler to generate assembly code from C code. All right, cool. So we cannot use register A anymore because it has the value of the right-hand side. So we use register B. Okay, so B is offset to px. Add BD. B is now the address of px. LD BB. So the B is the dereference of the address of px, which is really just saying the value of px. Now the value of px itself is a pointer. We don't really want to overwrite the pointer itself. We want to overwrite what the pointer is pointing to. So we need a store instruction at this point because B already has the right address to overwrite, and then register A has the right-hand side. So this completes our mission of changing whatever px is pointing to using the right-hand side of that expression. So from line 43 to line 50, we are implementing line 8 in the C code. And now we get to line 9. Okay, so to implement line 9, we need to store whatever register T has into register A. And someone may mention and go like, Tech, we don't have to do a single thing because line 43 and line 45 did exactly what we need to do at this point, and register A still has what we want to return as a return value. Well, that is actually true, but remember what I said. We'll pretend that we cannot retain register values from statement to statement in C. So now we're going to implement line 9, not assuming anything at all. So now we say we want A to be, so we always start with the offset. Okay, so we always start with the offset to whatever we want to access. We add the stack pointer to the offset, so it becomes an actual address to what we want to access. And then depending on whether we are storing or retrieving or passing as a parameter, we may or may not need an LD or ST instruction, but in this case we do, because we want to return the value of t. So this is the dereference of the address of t, which is really just the value of t, my local variable. And that completes the return value specification. And the rest of this subroutine is already done. Okay, we deallocate the local variables or variables or none. Okay, but depending on how many bytes we define to be my local variable size, local var size, this will do the deallocation correctly. We are adding whatever this amount is to the stack pointer, so the stack pointer will move up to a higher location, and hopefully back to where the return address is, because that's what we're assuming on line 59 is the stack pointer is now getting back to point to the return address. So we retrieve the return address, put it into register B, deallocate that location, and then continue execution in main. All right, so now we are going to deal with main, and the first thing we want to know is what does the stack look like from main's perspective. Now I understand that main is not called from any caller, so we can say there are no arguments. Okay, there are no parameters. Okay, fine. There's also no return address because remember main is not called in this particular architecture because we don't have an operating system. There's no libc or C library to call main. But we do have two local variables. So we have got I and j. So depending on the compiler, the ordering of the two local variables, usually I has the higher address. Whatever local variable is defined first has the higher address, and it keeps going lower and lower. So I and j should be like this on the stack, I having the higher address and j having the lower address. And because j is the last thing that we allocate on the stack pointer points to j. Now this is how we want the stack to look like. Doesn't mean that it looks like this at this point. So the first thing we need to do is to say how many local variables do we have in main. So main local var size is defined to be 2 because we need 2 bytes to store our local variables. Now that is just a label definition which does not change anything. Okay, it doesn't change the registers in any way at runtime. It is because a label is an assemble time concept. Okay, it is really just a name understood by the assembler to generate code. By itself, a label definition does not generate any code at all in the RAM file. So that means, in order for the stack to look like the way it is kind of pictured over here, I actually need to make it happen. Okay, the initialization of the stack pointer is implicit because all registers reset to 0 when we start executing a program. So we don't need to explicitly initialize the stack pointer, even though it's a good idea to do it, but it should not be done in main. It's not the job of a subroutine to do it. It is the job of the subroutine to allocate for the local variables that it needs. So we have a LDIA with main underscore local variable size, and then we subtract that much from the stack pointer. So we allocate for our local variables, and there we go. So I think this kind of answers the question for an earlier question of what is the ordering among the local variables of a subroutine. So because the stack looks like this, we then define j to be at an offset of 0 from where the stack pointer points to from main's perspective. And then I is just 1 byte above that. So it's 1, and then this 1 is the size of j. Okay, 1 plus. And because I is the last local variable to be defined in this particular manner, so instead of using a 2 over here, I can just refer to the label of the last local variable defined and the size of that last local variable, and then a plus. So this way, my local variable size is also going to float. If I need to define additional variables, especially if it's between I and j or before j, I don't need to change this definition at all because it is only reliant on label I. So it's basically floating as much as it can so that we can introduce additional local variables without having to change, um, or at least without having to hand compute the size of all the local variables. All right, so as I usually do, okay, I do this at the beginning and I'll do this at the end too. So I'm gonna just, oops, I need to paste it twice, and this time we need an add instruction to deallocate local variables, and I reverse the order. Sorry about that. So whenever I allocate for something, you better expect that I also deallocate the same thing when I'm done with this particular subroutine. Now, normally I would put a return code here, the 3 lines of code over here to return from a subroutine. But because main is not really called from someplace, so that's why I just put a halt instruction here, because it is not called, so there's nowhere to return to. So now in between, I can now implement line 16 and line 17 of the C code. So let me so we are already out of time for the allocated amount of time for today's lecture. So instead of just moving on to the lab portion, I'm going to finish this program, go through the trace analyzer, explain everything, kind of use up some of the lab time, because I think that is needed in order for you guys to get started with your program. So I'm going to use up some additional time, just kind of consider that as an extension of the lecture. So now we are on to line 16, and we're going to use the same approach that we have seen before. Okay, LDI, pick a free register. All 3 A, B, and C registers are free at this point, so I'm just going to use register A. I, so A is offset to I from the stack pointer. Add AD, so that A is now the address of I. And oh, that's the left hand side already, and we need another register to store the right hand side. So let's pick B to store the constant of 7. Okay, so B is the right hand side of the assignment, and now we can do the store. Okay, register A already has the address of my local variable I, and register B already has the right hand side of the assignment, so a single store instruction will initialize local variable I of main. So now we move on to line 17. Line 17 needs to call a subroutine. The first thing we need to do is to push the arguments on the stack. So we'll go ahead and do it. So first of all, we have to retrieve local variable I and then push it on the stack. Well, isn't that already in register B? The answer is yes. Okay, we could have just pushed register B on the stack, but we're going to do the whole thing, assuming that we know nothing about the registers on line 17. So we're going to have to do everything again. Okay, we start with I. So A is the offset to local variable I. Add AD, so the A is now the address of I. But this time we need an LD instruction, not a store. So the A is now the value of I. It's time to push it on the stack. Now, because computing the address of I and using the value of I are in the same statement, so we can do a little bit of optimization here. So instead of overwriting register A, which is now the address of I, I'm just going to use register B for the value of I. So we need to push that on the stack, which starts with a decrement D to allocate that 1 byte on the stack, and then the ST instruction to store whatever B has to the location that we have just allocated on the stack. So this is pushing I on the stack. Then we have the decrement D again, and then this time we store register A on the stack. Register A still has the address of I, and this is how we push it on the stack. So we have 2 arguments pushed on the stack at this point. It is now time to push the return address. So the usual way to do things is to like this. Okay, main return point 0. I usually define the label first so I don't forget. So LDI register A with main return point 0, decrement D, STDA. So this is pushing the return address. So this is the caller's perspective. From the caller's perspective, it has to push the arguments. Last argument pushed first, and then it has to push the return address. And once all three things are pushed on the stack, we can now do an unconditional branch to function f so that we continue execution in the subroutine. Now when the subroutine is done, excuse me, this belongs here. In other words, we have to branch first, and this is where it returns to. Now when it comes back to this point, okay, what is on the stack? Well, we still have the local variables of main on the stack because we know that is not going to be deallocated until when we are ready to get out of the program. But we still have the arguments on the stack. The subroutine is responsible to deallocate the return address, which was pushed by line 89. But the other two things, okay, pushed on line 84 and line 86, the two arguments are still on the stack. So it is important that we increment D twice, okay, to deallocate the arguments that have been pushed on the stack first. So that completes the invocation of F on the right hand side. And we can also assume register A has the return value of calling F with the address of I and the value of I, because that's the agreement, right? Because the agreement is register A is responsible to return a scalar value, okay? Now all the values are going to be scalar for this class. We are not going to return an entire structure, even though the programming language allows that. All right, so at this point we just have to store A to local variable J. So we have LDIJ, A with, nope, cannot use A because A already has a useful value. So B with J, so that B is offset to access local variable J. Add BD, so that B is now the address of J. And then we have a store instruction, B A, so that we are now storing to the dereference of the address of J, the right hand side, which is F of ampersand II, and we are done. Okay, so at this point this program is entirely done, and then the last few lines, line 99 and 100 are only here to deallocate the local variables used by main. So one question is, well, it doesn't seem like we are doing anything with the stack after this because it's just a single halt instruction. Do we really need to do line 99 and 100? Well, there are two answers. The first one is yes, we need to do this because conceptually every subroutine should deallocate its own local variables. So from the conceptual perspective, yes, we should do this. From the practical standpoint of, does it really change the execution of the program? Does it really change how this program is going to end? The answer is no, okay, because we have already stored correctly to both of the local variables of main. So whether we deallocate those bytes at the very end when it doesn't matter anymore would not actually change what we have done already. So the answer is yes and no. Now the third question is, if somebody is to forget to deallocate local variables in main when it's about time to exit, will points be deducted? The answer is a definite yes in that case, because conceptually it should be done, and as a result, when I am grading the final exam, I will take points off. Now it's not going to be a major deduction because I think somebody is just forgetting to do it instead of not knowing that it needs to be done, but nonetheless it will be points taken. All right, so now we got the whole thing working, and I just did something that I did not recommend you guys to do, which is um, to write a whole program before you test it. Okay, that is just not a very good idea because I have just written 101 lines of code without actually testing any of that in between. So that means if this program doesn't work, I have 101 lines of suspect code to go through when I try to debug the program. Okay, and that can be very daunting. So when you are writing your program, you don't want to write the entire thing. Okay, if you just want to get to a particular point, I'll show you what I mean by that. If you really just want to get to a point like maybe here, okay, on line 31, and you just want to see, okay, I just want to make sure that we got this part right, that we could access the parameters correctly, and we can dereference the parameters correctly, get to whatever px is pointing to and put it into register A. Well, guess what? You can always do this. Put a halt instruction right here, and maybe a reminder to tell yourself, okay, so as a to-do, just say that just for debugging, okay? So this way your program will stop midstream without running through the entire program, but it gives you a chance to debug your program step by step, okay? So you can always move this, further down, okay? If you got that one done, you just move it further down, rerun the program, check everything, make sure everything works, then move it further down again, and so on. Okay, so I do not recommend writing your program the way that I just did. Okay, when you are working on your lab. All right, so let's go ahead and run this code. So let me go do this cat pe.ttpsm pipe to xclip cell clip. Uh-oh, complaints about something. Cat pe.ttpasm. There we go. And now we can switch back to the assembler. There are a few steps we have to go before we get the program to run. All right, so we just do a paste here. So it's a good idea not to do editing inside the spreadsheet, because that can potentially cause issues. And then we go to the RAM file, which is right here, and download it. So we download as CSV, and we'll download it as pe.csv plus equal.csv. And then we go ahead and run the program in CLI mode, okay, command line interface mode. So I'll just go ahead and use my other window to do this. I'm just being lazy to go back to an earlier command. It's supposed this will work. TTY table load. It is called pe.csv, and then redirect the output to pe.tsv, like so. Press the enter key. Okay. Is that because I got the logic sim working? Nope. Error loading circuit file. Alright, so let me try to figure out why it's not loading it. That is not good. It's supposed to be there. Alright, so let's see if I have it still in the temp folder. Nope. Okay, so I just goofed, and we need to download it again. Nope, it's there. Oh, okay, I think I just did not specify the path correctly before. Yep, okay. Forgot that there's one more subfolder. That's okay. So we'll specify the rest of it. tty table dash load pe.csv and redirect to pe.tsv. There we go. All right, so now we have the trace, and we plug it into the trace analyzer. And just a recommendation, for writing and debugging a program for this lab, it's probably a good idea to kind of invest some time to look into how to get the trace analyzer thing to work, because it is a really useful tool for debugging a program like this. Without the trace analyzer, these kind of programs can be very, very difficult to debug. Okay. There we go. So just waiting for the there we go. So we got everything done. All right. So so now we are debugging a program that is 101 lines long, and I haven't debugged the entire program at all. So if you're doing this, I would suggest that you kind of go slow, with the debugging process. But I'm usually overconfident, so I'm going to go all the way to the end of this program and try to figure out whether it got something done correctly or not. So I can see that 0E is 14. Okay, E as a hexadecimal digit means 14 in base 10. So I can see that I store 14 into location FE. So now the question is, what is location FE? Now this is where a spreadsheet can be very helpful when you're trying to figure out what your program is supposed to do. Let me see, where's my spreadsheet? There we go. All right, so it is really helpful for you to really kind of get a handle on how the stack space is used, because otherwise you will have no idea whether FE is the right location or not. So we got location FF, FE, FD, FC, FB, FA, F9, and I think we got enough space at this point. So at the very beginning of this program, in main, we have to allocate for the two local variables, I and j, right? But the way we do the allocation is I has the lowest address, and then j has the, wait, I cannot remember, sorry. But that's okay, we can just look up the code here. So in main, oops, scroll down. All right, so in main, we use j as the one having the lower address and I being the one with the higher address. So that means j is where the stack pointer should be pointing at, and then I is 1 byte on top of that. So if I switch back to the spreadsheet over here, this is in main. Local variable I is the one that has the, I keep forgetting, I is the one that has a high address. So I is supposed to be here, local variable I. So I'm going to say, main local variable I. This is main local variable j. And so overwriting location FE with 14 is actually correct. Okay, So if I go back to the trace analyzer and look at this particular row here, it's overwriting location FE with the value of 0E. That is good. Okay, that the program works up to this point. And when I look at this line over here, register D, which is the stack pointer, is going back to point to location 0, 0. That's good too, because this is what we want the program to do, because whatever the stack pointer value is at the beginning of main, we want it to end up with exactly the same value. So D equals to 0, 0 is good. We also know this program at some point in its execution is supposed to change local variable I of main to the same value of 14. So now we look in column C for that particular event. And there we go. Okay, so all the really important side effects of running this program can be observed in this trace. So this trace is good from the perspective of I can now see that the program works. However, it is not good from the perspective of I don't have a way to show you how to debug your program because the program works. I was kind of hoping that I would make a mistake somewhere that causes the program not to work. Then I can show you what the trace would look like and how to diagnose the program when it's not working. But that's okay, because what you can do, I'm going to give you everything. So right now, at this point, and I'm not going to change the assembler nor the trace analyzer for at least the next hour or so, maybe for the rest of today. Unless one of you have a program for me to take a look, then I might change it. So now would be a good time to take a snapshot of the assembler. Okay, just make a copy of the assembler at this point. It has got the program, it has got the RAM file already done. So just make a snapshot of the entire spreadsheet. Just copy it to your own Google Drive. So now you have a copy of that. And at the same time, make a copy of the trace analyzer. You might want to just create a subfolder within your Google Drive so you can just stash everything related to today's lecture into the same folder. So this way, you know all of that stuff belong together. Okay, and what I will also do is to upload the programs that I have just written today onto Discord. So I'm going to add let me see if I can select multiple items. I think I can select multiple items. It's just that it doesn't, it wants me to comment on those separately. Nope, that's not what I want to do. I'm just working on Discord right now. Alright, so we got the C file, then the TTPASM file. There we go. There we go. So I have just uploaded the C code and also the assembly code to Discord. So I'm gonna pin it first, and then I'll go back. I have a little bit more to say about this program and what you can do, because I got everything uploaded, so you got all the resources at this point. But I also want to point out what you can do at this point. Okay, now we know this program works, okay, because I have just verified, even though I did not verify every single line. But if I can get to those 3 conclusions, register D got back to 0, we got to the end of the program, the halt instruction, without any problems, and the 2 locations in RAM that are supposed to be changed were changed, and they were changed correctly. So all of those, kind of points to the direction that the program worked fine. Okay, so we know this program works okay. So what you can do is to go through this program when you might be watching the video again. So as you go through this program, kind of look at the concepts. Okay, that's one thing, but you can also just kind of go between the trace analyzer and the assembler. Okay, so So that's why I think it is important to make a copy first. And you go to the program, you go to the part of the program where things start to get a little bit interesting. So let me go to the Assemble tab. The Assemble tab is usually very helpful because it doesn't just show you the source code, but it also shows you the instructions, how the labels are defined, what are the actual bytes being moved, and so on. So using this view can be helpful, when you're looking at the Assemble tab. So you could just kind of scroll through the program and you get to a point where you ask, okay, I'm not really quite sure what this is doing. So let's just say, that this is the instruction, and go like, I don't know why this code works. Okay, I don't know why this is allocating for the local variable. What is being done to register D? What was the value of register D, the stack pointer before, and how is it after, blah, blah, blah. Okay, so let's just say that this is what we want to figure out. Column W tells you the address of the opcode, which is 05 in this case. Then you go to the trace analyzer, and because we are not dealing with a loop nor recursion in this case, so 05 should show up only once in column A. So you go to 05, which is right here, okay? And you can see the effect of this subtraction instruction is changing register D. So register D was FB before, and it is now updated to FA. So we just subtracted 1 from the stack. The question is, what is on the stack at this point? Okay, so how do we answer that question? What is on the stack at this point? And how did those items appear on the stack? That is the job of column C. Column C will show you the update of locations in RAM. So you can see FB, location FB, has a value of 3E. Then the next immediate question is, who put it there and what does it mean? Okay, what is the point of storing 3E at location FB? And it is done by the opcode at location 3B. So those are the questions that I would ask. Okay, so to answer those questions, you look at location 3B with the execute at, which is basically just the program counter. You look up the Assemble tab in the assembler, and you try to look up 3B in this case in column W. So scroll down. This is location 3B. Okay. So 3E is pushed on the stack because of this particular instruction. So why do we push 3E on the stack? Well, 3E is coming from the LDA instruction. The LDA instruction is just loading main underscore return 0 into register A, which eventually got pushed on the stack, by the instruction that we just observed in the trace analyzer. And the label is really just a continuation label so that the subroutine knows where to continue execution. So that is really the return address. So when you look at the trace analyzer and you look at this code, this is the return address. So what else can we do about this? You can maintain your own spreadsheet. So this is my own spreadsheet. It is not in Google Sheet. So now we go to location FB and just say that this is how the return address back to main. Okay, so by doing it this way and by looking at the trace of the program backwards, you can now figure out what content, what value got into which part of the stack. And you can look up the opcode or the location of the opcode, use the assembler, figure out which opcode it is, and understand the context of that opcode. This is supposed to push the address of I from main. Okay, so now we go back to the spreadsheet and just say that this is the address of I in main. And this is actually the value of I in main. And let's make it a very clear value of main I. So this is how you can look at the trace, look at the assembler, and have your own spreadsheet to basically restitch the content on the stack with an explanation after each location. I think if you were to do this for the program that I demonstrated today, that really will help you understand the concept that we talked about today. I understand there's a lot of stuff that we talked about today, but out of that, a lot of stuff, the core concepts are actually just a few. Okay, it's basically how we utilize what we call a frame, on the stack, and how items, parameters, the return address, and local variables are allocated on the stack. So those are the core concepts. The program is a little bit long, but if you look at the program, okay, let me just look at the program again. Even though it is long, there's a particular format to it. The format is we load the offset into a register, we add the stack pointer to that same register. That's how we compute the address of a particular item in the frame. Then, depending on what we intend to do with that thing, we might have an LD to dereference, from reading that location, or we might have an ST to store into that location. Because once you get to the address of an item on the frame, you can read from it, you can write to it, but when you read from it, you might have some additional LD instruction because what you retrieve may be a pointer itself. If what you have just retrieved is a pointer, then you can dereference again, but every time you dereference, you can either read as a dereference or you can write as a dereference. So that determines whether you're reading or writing or loading or storing. So that concept is really just used repeatedly throughout this entire code. If you notice that pattern, that's great, because that's really the point of today's lecture, is how things are organized on the stack and how we access those items. So I think I'm finally done with the lecture. Are there any immediate questions before I take a 10-minute break and then I can come back to Discord? There are 5 of you still sticking around, not counting people who might be watching the YouTube part of it. So does anyone have any questions before I move on? The code for the lab. Oh, right. Forgot about that. I think it is just swap, but let me check. I think Richard has tried it already and is reporting back. And I have to push the due date too. I think I got the... No, it's correct. 23rd is the correct one. So it's due on Thursday. And Richard is asking if we manually put in the offset of each variable. Yes, that will work too. It's just not as flexible. So if you need to change your program later on, then you have to remember to update everything. It's not, they're not relative to each other. But otherwise, yes, you can always do it with just constants. Yep, the passcode is indeed just a swap. So let me just type it here. There we go. And pin it. All right. Thought Sakio was typing earlier in Discord, so let me just kind of wait until that message shows up. Yeah, so there's a lot to review, but as I said, the concepts, there are only a few really key concepts. The program is long because there's a lot of repetition. So the idea is not to think of that program as a really long, complex program, but to think of that program as an illustration of the key point of today's lecture, which is basically how things are organized on the stack. And to help understand that, having a spreadsheet like this, on your own, okay, this is your own spreadsheet that you can use Excel, you can use LibreOffice, you can even use Google Sheet, to make it easy to deal with, so you don't need to install any spreadsheet programs. But to have a map like this, to kind of understand as you execute the program mentally, what is being allocated and what is sitting where on the stack, that is going to be helpful. Also, if you maintain a map like this, in terms of the memory map, when you want to ask me and clarify something, this would be very helpful, because if you can show me what you have understood up to this point, and have a map, and then you ask me, okay, but I'm not quite getting where this item is relative to everything that I have already figured out on the stack, that gives me the context of how to answer the question. So that is going to be helpful as well. For those of you who don't want to use the trace analyzer because you don't want to deal with running Logisim on the command line interface, one thing you can do, okay, in that case, not really recommended, because I really think that the trace analyzer is a better way to get things done. But if you are saying, I don't want to do that, okay, I want to use just the GUI mode of Logisim, but I want to be able to kind of track what this program is doing, up to a certain point. You could do it this way. It is very tedious, but you can do it this way. Okay, so let's just say that you want to understand what the stack looks like right before we continue execution in the subroutine, right before the JMP-IF instruction here. I suppose you could do this. Do it this way, put a halt instruction right before that. Okay, so this way, when you run this program, when you assemble, download, put it into Logisim and run it in Logisim in GUI mode, it will stop execution right at this halt instruction, because it will encounter this halt instruction way before the other halt instruction. So the program will stop, and then at that point you can look into the content of RAM, you can look at the registers and try to figure out why the stack looks the way it does at that point in time. The problem with this approach is it is really kind of tedious, because the moment you want to say, I want to move on and debug the program further down, maybe somewhere in the subroutine, okay, then you have to move the halt instruction into the subroutine where you want it to be. Okay, so let's just say that you want to see what it looks like at this point. Then you have to reassemble the program, download it again, put it into the RAM in Logisim, run it, stop, take a look at the RAM content, take a look at all the registers, then you move it somewhere else and repeat the whole process. I think in the long run, it is very time consuming compared to learning how to run Logisim on the CLI, on the command line interface, because once you learn how to do that, you collect the trace, once and for all. Okay, this is the entire trace of running this entire program. Okay, and you don't have to do it in an interactive mode, because you can just kind of scroll through the whole thing and try to figure out what the program is doing, each step along the way. There's one more thing. Okay, I know most of you are thinking, okay, I'm ready to take a break. So am I. But there's one more thing. Okay, the one more thing is kind of interesting if you have the time. Now we know this program works, so every line of code is correct. So now the question is, what if I forget something? What if I were to make a mistake somewhere? What if I to forget about this add AD instruction? What is the program going to do without this add AD instruction? So you can now start to break a previously working program to observe the symptoms of making very specific errors in this program. Now, in the long run, this is going to be helpful. Now, don't do this, from the get-go, okay? But once you start to understand how this kind of code works, an interesting thing to do is to intentionally break the program, because you know how the program is broken. You're just trying to observe the symptoms when the program is broken in that particular way, that also helps you to understand the content of this class. Is basically just intentionally breaking something and see what happens when it's broken. All right, so I think I'm really ready to stop live stream at this time, but I will come back in about 10 minutes, and I'll stay on the text channel for at least another hour and a half. So if you're reviewing the material and you have specific questions about what we talked about today, I'll be here to answer those questions. All right, so I will disconnect the